There was a time long before the Earth existed, long before the sun itself had ever burned, when the space that would one day become our solar system held nothing recognizable as a beginning. No light, no warmth, no planets circling anything at all. Only a vast, quiet cloud, drifting through the greater darkness of the galaxy, patient and unremarkable, one of countless such clouds scattered across the Milky Way, each indistinguishable from the next. This cloud was made of the simplest ingredients the universe has to offer: hydrogen, by far the most abundant, the same element that fuels every star. Helium, formed alongside hydrogen in the earliest moments after the Big Bang. And scattered sparingly throughout, in quantities so small they might seem almost negligible, heavier elements: carbon, oxygen, iron, silicon, the remnants of stars that had lived and died long before this particular cloud ever began to stir. Every one of these heavier atoms had once been forged inside the crushing heat of some earlier star's core, or scattered outward in the final violent moments of that star's death. In this sense, the cloud we are describing was never truly new material. It was recycled matter, ancient in its origins, patiently waiting to be given new form. To call this collection of gas and dust a cloud is, in some ways, a generous description, at least by the standards of anything we might picture when we imagine clouds here on Earth. This was not a dense, billowing formation like something drifting across a summer sky. It was extraordinarily thin, its particles spread so sparsely across such enormous distances that, by many measures, it was closer to a vacuum than to anything we would recognize as substantial. And yet, despite this thinness, the scale involved was almost impossible to properly hold in the mind. Clouds like this one commonly stretch across many light years, distances so vast that light itself, moving at its full and constant speed, would require years simply to cross from one side to the other. Picture for a moment drifting slowly through the heart of such a cloud, if such a thing were somehow possible. There would be no clear boundary to mark where it began or ended, no dramatic wall of visible material announcing its presence. Only a gradual thickening of near emptiness into something faintly less empty, gas and dust so finely dispersed that entire regions might pass unnoticed by an observer without sensitive instruments capable of detecting what the unaided eye could never see. It is a strange kind of setting for a birth to eventually take place. Not a dramatic stage, lit and ready, but an unassuming stretch of near nothing, waiting, without any awareness of waiting, for a story it did not yet know it would come to hold. Within clouds like this one, scattered across the galaxy in their uncountable numbers, most simply persist for long stretches of time, drifting, slowly shifting, without any dramatic transformation ever taking place. The vast majority remain exactly what they have always been, quiet reservoirs of ancient material, contributing nothing further to the universe beyond their own continued, uneventful existence. Only a small fraction of these clouds will ever undergo the kind of change that leads towards something as significant as a star, let alone an entire system of planets circling that star. And of that fraction, fewer still will happen to produce anything resembling the particular arrangement we find ourselves within today, a star of just the right size and temperament, planets settled into just the right range of distances, conditions eventually suitable, against considerable odds, for something as improbable as life itself to take hold. This particular cloud, the one that concerns our story, held no special markers to suggest it was destined for anything beyond ordinary persistence. Nothing about its composition, its size, or its location within the galaxy set it clearly apart from countless similar clouds nearby. If some outside observer had been able to survey the region at that time, cataloging every molecular cloud within reach of their instruments, this particular cloud would very likely have registered as entirely unremarkable, one among many, worthy of no special attention whatsoever. And yet here we are, every mountain range, every ocean, every living creature that has ever drawn breath, every one of us listening now to this account of a beginning so distant it can barely be comprehended, all of it eventually traces back to material drifting somewhere within a cloud precisely like this one. The atoms that would someday form your own body, whoever is listening to this now, were already present, scattered, thin and unremarkable, somewhere within a slowly turning cloud of gas and dust, long before there was any earth to walk on, any sun to warm it, any sky to hold stars at all. There is something worth sitting within that fact, something that resists easy summary. We tend to think of our origins in relatively modest terms, tracing backward through generations of ancestors, then further still through the slow unfolding of evolution, arriving eventually at the first stirrings of life on a young and hostile Earth. But the true beginning of our story reaches back considerably further than even that. It reaches back to a cloud of dust and gas, adrift in interstellar space, made of material older than the sun itself, older than any planet, older in truth than everything else contained within this particular account we are about to follow. For a very long time, and in cosmic terms, this stretch of relative stillness could last for millions of years without any significant change. This cloud simply continued as it always had. Gravity, weak as it is across such enormous distances, worked quietly and continuously, an ever-present but exceedingly gentle force, pulling every particle within the cloud very slightly toward every other particle. In most cases, this gentle pull accomplishes very little, easily balanced by the cloud's own internal motion, its particles drifting and colliding in ways that prevent any significant collapse from actually taking hold. But balance, however stable it may appear across long stretches of time, is rarely permanent. Somewhere within this particular cloud, something was eventually going to shift, however slightly, and once that shift occurred, gravity would finally begin to gain a foothold it had never quite managed to secure before. What exactly might have triggered such a shift remains, even now, a subject of careful scientific investigation rather than settled certainty, though several plausible possibilities exist, each consistent with everything we currently understand about how stars are born. We will turn to that shift and to what set it into motion shortly. But for now, it is enough to simply remain within this quiet, patient scene a little longer. A vast, nearly invisible cloud, spread thin across a distance the mind can scarcely hold, made of material recycled from stars that lived and died long before it ever existed, containing within its scattered atoms everything that would eventually become not just a star and its planets, but every living thing those planets would ever come to hold. Nothing about this moment looked like a beginning, and yet quietly, unremarkably, without any fanfare the universe would ever record, this was exactly where our story actually starts. Stability within a cloud of interstellar gas and dust is rarely as permanent as it appears across any single stretch of observation. For as long as such a cloud remains in a state of rough equilibrium, its own internal motion, the constant, chaotic drifting and colliding of its particles, works to counteract the slow, patient pull of gravity attempting to draw everything inward. This balance can persist for a remarkably long time, measured not in years or centuries, but often in millions of years, the cloud continuing much as it always has, changing so gradually that any transformation remains essentially undetectable across ordinary human timescales. But equilibrium of this kind, however durable it may seem, depends on a delicate balance of forces that can be disrupted by relatively small disturbances. And within the broader galaxy, disturbances of exactly this kind are not particularly rare. It is to one of these disturbances, or more precisely, to the general category of disturbance scientists believe most likely to have affected the particular cloud in our story, that we now turn. The most widely supported explanation for what disrupts the equilibrium of a molecular cloud like this one involves an event considerably more dramatic than anything occurring within the cloud itself: the death of a nearby star, ending its life in the catastrophic explosion known as a supernova. When a sufficiently massive star exhausts its nuclear fuel, it can no longer sustain the internal pressure that has, for millions or even billions of years, held it in balance against its own gravity. The result is a collapse followed by an explosion of extraordinary violence, briefly outshining entire galaxies, and releasing a shockwave that travels outward through surrounding space at tremendous speed. If such a shockwave happens to pass through a nearby molecular cloud, one that has, until this moment, remained in its own quiet, stable balance, the effect can be significant. The wave compresses the gas and dust it encounters, pushing particles closer together than they had been before, disrupting the delicate equilibrium that had previously prevented the cloud from collapsing under its own gravity. In certain regions within the cloud, this compression can push local density past a critical threshold, a point beyond which the cloud's own internal motion is no longer sufficient to resist gravity's pull. Once this threshold is crossed, collapse becomes not merely possible, but effectively inevitable. It is worth acknowledging, with the same scientific honesty this account has tried to maintain throughout, that a supernova shockwave is not the only mechanism capable of triggering this kind of collapse. Other possibilities exist as well, including simple gravitational instability arising within an unusually dense region of the cloud itself, without any external trigger required at all, or disturbances caused by the cloud passing through a spiral arm of the galaxy, where gravitational forces are somewhat stronger than in the surrounding regions. Scientists studying the specific chemical signatures found within ancient meteorites, ones that formed very early in our solar system's history, have found evidence, though not entirely conclusive, suggestive of a nearby supernova as a plausible trigger for our particular cloud's collapse. This evidence remains a matter of ongoing scientific investigation rather than fully settled fact, and it is offered here not as certainty, but as the most well-supported explanation currently available. Whatever the precise trigger may have been, the underlying process that followed remains consistent across every plausible scenario, and it is this process, rather than the specific trigger itself, that carries the greater significance for the story we are following. Somewhere within the cloud, a region of gas and dust, having been pushed past the delicate threshold that had previously maintained its equilibrium, began, very slowly at first, to collapse inward under the pull of its own gravity. It is difficult to overstate just how gradual this beginning truly was. There was no dramatic instant of transformation, no clear moment at which an outside observer might have pointed and declared that something significant had just occurred. Instead, across a span of time reaching into the tens of thousands of years, this particular region of the cloud began contracting, almost imperceptibly, its particles drawing very slowly closer together, the whole process unfolding with a patience that defies almost every intuition we carry from our own comparatively brief human experience of time. As this slow contraction continued, something else began happening as well, a subtle shift with consequences that would ultimately shape everything that followed. Even the faintest, most negligible rotation, present within nearly any large cloud of gas and dust as a simple consequence of its interactions with the broader galaxy, would inevitably become more pronounced as the cloud's material drew closer together. This effect follows directly from a fundamental principle of physics, one that governs everything from a spinning ice skater to the rotation of an entire collapsing cloud: conservation of angular momentum. As the radius of any rotating system decreases, its rotational speed must correspondingly increase, in order to preserve the same overall angular momentum the system possessed before it began contracting. We will explore this particular effect and its extraordinary consequences in the chapter that follows. For now, it is enough to understand that this slow, barely perceptible collapse, triggered by forces working across scales that make our entire planet seem impossibly small by comparison, marked the true beginning of a transformation that would, over an immense span of time, eventually give rise to a star, and to everything that star would come to hold in orbit around it. There is something worth pausing on here, something easy to overlook amid the physics and the careful scientific caveats this account has tried to maintain. What we are describing in this quiet, gradual collapse is not simply an abstract astronomical process, distant from anything relevant to our own existence. This was the beginning of everything that would eventually become the sun and earth and every living thing earth would ever hold, ourselves included. And it began not with any dramatic announcement, but with something closer to a whisper, an almost imperceptible shift within an already largely unremarkable cloud, disturbed perhaps by the distant death of some other star entirely, one whose name, whose exact nature, whose precise location remains unknown to us even now, and likely always will. Somewhere within that slow, patient contraction, gravity had finally gained the advantage it had waited so long to secure. And though nothing about this moment would have appeared significant to any observer capable of witnessing it directly, everything that followed, every subsequent chapter of this long, unfolding story, depended entirely on this quiet, unassuming beginning having taken place exactly as it did. The cloud was no longer simply drifting. It had begun, slowly and irreversibly, to fall inward, toward a center that did not yet exist, but which its own gradual collapse was already, patiently, beginning to create. There is a particular kind of grace that emerges from even the simplest laws of physics, a grace that becomes especially apparent when we turn our attention to what happens as a collapsing cloud of gas and dust begins, ever so slowly, to spin faster. This effect, though it follows from principles simple enough to be demonstrated with nothing more than a spinning chair and an outstretched pair of arms, would ultimately shape the entire architecture of what our cloud was about to become. The principle at work here is known as conservation of angular momentum, and though its name carries a certain technical weight, its underlying logic is remarkably intuitive once properly understood. Angular momentum describes, in essence, how much rotational motion a system possesses, a quantity determined jointly by how fast something is spinning and how far its mass is distributed from the center of that spin. Crucially, in the absence of any outside force acting to change it, this quantity remains constant, conserved, even as other aspects of the system shift and change around it. Picture for a moment an ice skater beginning a spin with her arms stretched wide. She rotates at this stage relatively slowly, her mass spread outward from her body's central axis. But as she draws her arms inward, pulling them close against her body, something remarkable happens, something many of us have watched countless times without necessarily reflecting on the physics quietly at work. She spins faster, considerably faster. Nothing about her total angular momentum has changed in this maneuver, but by reducing the distance between her mass and her axis of rotation, she forces her rotational speed to increase correspondingly in order to preserve that same underlying quantity. Our collapsing cloud, vast as it was compared to any human skater, obeyed this exact same principle, playing out now across a scale almost impossible to properly picture. As gravity drew the cloud's scattered material closer and closer toward its center, the cloud's rotation, faint and barely perceptible in its earlier, more diffuse state, began to noticeably accelerate. What had once been an almost undetectable drift, a rotation so slow it would have taken enormous patience and precision instruments merely to confirm its existence at all, gradually transformed into something considerably more pronounced, the collapsing material spinning faster and faster as it continued drawing inward toward an increasingly dense, increasingly defined center. This acceleration in rotation carried with it a second consequence, one just as significant as the increase in speed itself. A rotating system, particularly one collapsing under its own gravity, cannot simply continue contracting uniformly in every direction indefinitely. The very act of spinning introduces a kind of outward force, working in opposition to gravity's inward pull, a force that becomes increasingly influential precisely along the plane of rotation, even as it offers little resistance to material collapsing along the rotational axis itself, the imaginary line running directly through the system's center, perpendicular to its spin. The practical result of this interplay between gravity and rotation is a transformation in shape, one that occurs gradually, but with a kind of quiet, mathematical inevitability. Material collapsing along the rotational axis encounters relatively little resistance, continuing to fall inward with comparative ease, contributing to an increasingly dense, increasingly hot region forming at the system's very center. Material attempting to collapse along the equatorial plane, however, the region extending outward from that same center in the direction the system is actually spinning, encounters considerably more resistance, held outward, at least temporarily, by the very rotational motion that continues to intensify as the collapse proceeds. The result of these competing tendencies is a shape that over time becomes unmistakably distinct from the roughly spherical cloud that first began this collapse. What was once a diffuse, three-dimensional cloud, extending roughly equally in every direction, gradually flattens, drawing inward along its poles while retaining considerably more material along its equatorial plane. This flattening produces something close to a disk, though not yet the fully formed structure that would eventually earn the name protoplanetary disk. At this earlier stage, we might more accurately describe what is forming as a protostellar disk, a rotating, flattened structure of gas and dust, surrounding an increasingly dense, increasingly significant concentration of material gathering at its very center. This center deserves particular attention because it represents, quite literally, the seed from which our entire solar system story would eventually grow. As material continued falling inward from the surrounding disk, drawn by gravity toward this central concentration, the region grew steadily denser, its particles pressed closer and closer together, colliding with increasing frequency and, crucially, with increasing energy. Each collision, however minor in isolation, contributed a small amount of heat to the growing central mass, a subtle but steadily accumulating warming effect that would ultimately prove essential to everything that followed. It is worth pausing here to appreciate the strange, almost paradoxical relationship between collapse and heat that characterizes this entire process. One might reasonably assume that a cloud of gas, cold and diffuse as it begins, would simply remain cold as it contracts, its temperature unaffected by the mere act of drawing closer together. But this assumption, intuitive as it may seem, does not hold true. As gravitational potential energy, the energy stored simply by virtue of the cloud's particles being spread apart across a wide distance, converts into kinetic energy during the collapse. That kinetic energy manifests at the level of countless individual particle collisions as heat. The very act of falling inward, in other words, generates warmth, a warmth that becomes increasingly concentrated and increasingly significant as the central region of the collapsing cloud continues to grow denser. This growing central concentration, still not yet a star in any meaningful sense, but no longer simply an undifferentiated clump of gas and dust either, is generally referred to by astronomers as a protostar, a term reflecting its intermediate status, no longer part of the diffuse, quiet cloud from which it originated, but not yet possessed of the defining characteristic that would ultimately transform it into something capable of shining under its own power. Around this growing protostar, the surrounding disk continued its own quiet evolution, spinning steadily, flattening further, its material gradually settling into the rough, disc-like structure that would eventually provide the raw material for everything else our solar system would come to hold. Within this disk, though its full significance would not become apparent for a considerable time yet, lay the scattered ingredients not just of planets, but of moons, asteroids, comets, and every other body that would eventually find its place within our solar system's eventual architecture. For now, though, the central protostar remained the primary focus of this unfolding transformation, continuing to draw material inward, continuing to grow denser and warmer with each passing century, moving slowly but steadily toward a threshold that, once crossed, would mark one of the most significant transitions in this entire patient story. That threshold and the dramatic, if still relatively quiet, transformation it would bring about awaits us next. There exists within the deep interior of any collapsing protostar a particular threshold, one defined not by any external marker, but by the fundamental physics governing matter itself under conditions of extraordinary pressure and heat. As our own protostar continued contracting, drawing ever more material inward from its surrounding disk, its central temperature and pressure climbed steadily higher, following a trajectory that would, given sufficient time and sufficient accumulated mass, inevitably lead toward this threshold, whether or not anything within the collapsing cloud possessed any awareness of what lay ahead. To understand what this threshold actually represents, it helps to consider what happens to matter when subjected to truly extreme conditions considerably beyond anything encountered in ordinary experience here on Earth. Deep within our protostar's core, temperatures had, by this stage, climbed into the millions of degrees, while pressure had grown correspondingly immense, the accumulated weight of all the material surrounding this central region pressing inward with tremendous, unrelenting force. Under conditions this extreme, hydrogen atoms, the most abundant element within the collapsing cloud from the very beginning, found themselves compressed so tightly, moving with such tremendous energy, that they began, with increasing frequency, to collide with a force sufficient to overcome the natural repulsion that would ordinarily keep their positively charged nuclei safely apart. When hydrogen nuclei collide with sufficient force to overcome this repulsion, something remarkable occurs, a process known as nuclear fusion, in which the colliding nuclei combine to form a heavier element, helium, releasing in the process an extraordinary quantity of energy. This energy release follows from one of the most significant relationships in all of physics, the equivalence between mass and energy, meaning that even a very small amount of mass, when converted through fusion, yields an amount of energy that can seem almost disproportionate given the tiny scale of matter actually involved. Once fusion reactions of this kind begin occurring with sufficient frequency and consistency throughout a protostar's core, something has fundamentally changed, a transition significant enough that astronomers consider it the true, defining birth of a star. The protostar, having spent its entire existence up to this point relying solely on gravitational collapse to generate whatever heat it possessed, now had an entirely new, considerably more powerful source of energy actively burning at its very center. Our protostar, after this transition, was no longer merely a dense, warm clump of collapsing gas. It had become, in every meaningful sense, a genuine star. Our sun had ignited. It is worth taking a moment to appreciate the profound significance of this particular transition, one that separates, in the clearest possible terms, everything that came before from everything that would follow. Every subsequent chapter of our solar system story depends entirely on this moment having occurred successfully. Without sufficient mass accumulating within the collapsing cloud to generate the pressure and temperature required for fusion to begin, our protostar would have remained forever as it was, a warm but ultimately inert object, sometimes referred to as a brown dwarf, incapable of producing the sustained light and heat that would eventually allow planets and life to exist at all. But our particular protostar did possess sufficient mass, and fusion did successfully ignite within its core, marking the moment our solar system finally acquired the star at its center that would go on to define nearly everything else about its subsequent evolution. It is worth noting, however, that the Sun in this earliest stage of its existence bore only a partial resemblance to the steady, reliable star we depend upon today. Young stars of this type, still surrounded by the remnants of their formative disk, still adjusting to the newly established balance between the inward pull of gravity and the outward pressure generated by ongoing fusion, tend to pass through a particularly turbulent early phase, one astronomers refer to as the T-Tauri stage, named for a prototypical young star first studied in detail for exhibiting exactly this kind of behavior. A T-Tauri star differs considerably from a mature, stable star like the Sun we know today. Its brightness fluctuates far more dramatically, sometimes flaring with sudden, unpredictable intensity, driven by magnetic activity considerably more vigorous than anything our present-day Sun typically exhibits. Its stellar wind, the continuous outward stream of charged particles that every star produces to some degree, blows considerably stronger during this early phase as well, a powerful, turbulent outpouring of energy and material that would, in time, play a significant role in shaping the very disk from which the star itself had only just emerged. This early stellar wind deserves particular attention, because its effects would prove essential to nearly everything that happened next within our still-forming solar system. As the young sun's wind intensified, it began pushing outward against the surrounding protoplanetary disk, the flattened structure of gas and dust that continued encircling the newly ignited star. This outward pressure would, over time, begin clearing away much of the disk's remaining gas, particularly in regions closer to the sun itself, a gradual dispersal that would eventually determine, in ways we will explore across the chapters ahead, exactly how much raw material remained available for the formation of planets, and precisely what kind of planets that remaining material would ultimately produce. For now, though, it is enough to simply witness this remarkable transition in its own right, setting aside for a moment its later consequences. At the very center of what had once been an entirely unremarkable cloud of interstellar gas and dust, drifting quietly through the galaxy for who knows how long before some distant disturbance finally set its collapse into motion, a star had now ignited. Light produced through genuine nuclear fusion rather than merely the residual heat of gravitational collapse began radiating outward in every direction, illuminating, for the very first time, the swirling disk of material still encircling this newly formed star, material that had, until this moment, existed only within darkness, however faint and diffuse that darkness might have been. There is something worth pausing on here, something easy to overlook amid the physics of fusion and stellar formation. This moment, however distant, however abstract it might seem when described in the careful, measured language of astrophysics, represents the true birth of the very star that would, across the billions of years to follow, provide every bit of warmth and light that life on Earth would ever come to depend upon. Every sunrise you have ever witnessed, every warm afternoon, every quiet evening spent watching a sunset fade slowly into darkness, ultimately traces back to this singular, transformative moment, when a collapsing cloud of ancient, recycled stellar material finally grew dense and hot enough at its center to ignite the nuclear furnace that continues burning, steadily and reliably, at the very heart of our solar system to this very day. The sun, now genuinely a star rather than merely a collapsing protostar, would continue this early, turbulent phase of its existence for a considerable span of time yet, its light and its powerful stellar wind steadily reshaping the disk of gas and dust still surrounding it. Within that disk, though nothing yet resembling a planet had begun to take shape, the raw ingredients for an entire system of worlds remained scattered, waiting patiently for the next chapter in this long, unfolding story of formation to finally begin. With the sun now genuinely ignited, burning steadily through nuclear fusion at its core, our story's focus shifts outward, away from the star itself and toward the vast, swirling structure that continued to encircle it. This structure, the protoplanetary disk, deserves careful attention in its own right, because it was here, within this thin, rotating plane of gas and dust, that everything else our solar system would eventually contain. Every planet, every moon, every asteroid and comet first began its long, patient process of formation. To properly picture this disk, it helps to set aside any image of neat, orderly rings, the kind we might imagine when picturing something like Saturn's rings today. In these earliest stages, the protoplanetary disk was considerably less defined, a broad, flattened distribution of material extending outward from the young sun across a distance that would eventually encompass the orbits of every planet our solar system would come to hold, and considerably beyond that as well. Within this disk, gas dominated by sheer quantity, primarily the same hydrogen and helium that had made up the bulk of the original molecular cloud, but scattered throughout this gas, in relatively small but critically important proportions, drifted solid particles of dust, tiny grains composed of silicates, metals, and various ices, the accumulated remnants of long-dead stars, now repurposed as the raw building material for an entirely new system of worlds. The disk structure was not uniform throughout its extent, and this variation would ultimately prove enormously significant for everything that followed. Closer to the young sun, temperatures remained relatively high, heated directly by the newly ignited star's radiation. Only materials capable of remaining solid under these warmer conditions, primarily various metals and rocky silicate compounds, could exist as solid particles this close to the sun. Water, along with other compounds we generally think of as ices, methane, ammonia, and carbon dioxide among them, simply could not remain frozen in this warmer inner region. Instead, these compounds existed only as gas, unable to contribute to the accumulation of solid material occurring nearby. Farther out from the sun, however, conditions shifted considerably. Beyond a certain distance, one that varied somewhat depending on the specific compound in question, but which astronomers generally treat as a single meaningful threshold, temperatures dropped low enough that water and other volatile compounds could exist as solid ice rather than gas. This boundary, marking the transition between the warmer inner disk and the colder outer disk, is known as the frost line, sometimes also called the snow line, and its exact location would prove to be one of the single most consequential features of the entire protoplanetary disk, shaping, in ways we will explore across the chapters ahead, why the planets that eventually formed on either side of this boundary turned out to be so dramatically different from one another. Within the inner disk, then, closer to the sun and warmer as a result, only rocky and metallic material could accumulate as solid particles, everything else remaining as gas, largely unable to contribute directly to the formation of anything solid in this particular region. Beyond the frost line, however, in the colder outer reaches of the disk, both rocky material and vast quantities of ice existed together as solid particles, dramatically increasing the total amount of solid material available for accumulation in this more distant region compared to what remained available closer to the sun. This distinction between inner and outer disk, seemingly a relatively simple consequence of basic temperature variation, would ultimately determine an enormous amount about the eventual architecture of our solar system. But we are getting ahead of ourselves slightly, reaching forward toward consequences that properly belong to later chapters in this unfolding story. For now, it is enough to simply appreciate the disk itself, in this relatively early stage of its existence, as a vast, structured reservoir of raw material, gas and dust distributed unevenly according to distance from the young sun's growing warmth, waiting patiently for the slow processes of accumulation that would eventually transform scattered particles into substantial worlds. It is worth pausing here to consider the sheer scale involved in this disk, because it can be remarkably easy to underestimate just how vast a structure we are actually describing. The protoplanetary disk that once surrounded our young sun extended across a distance considerably larger than the orbit of Neptune, the outermost planet our solar system would eventually come to hold. Within this enormous span, the total quantity of solid material, the dust and ice grains that would eventually accumulate into planets, moons, and countless smaller bodies, represented only a very small fraction of the disk's overall mass, the vast majority still composed of hydrogen and helium gas, material that would, in time, either become incorporated into the atmospheres of the largest planets, or else be gradually swept away entirely by the young sun's increasingly powerful stellar wind. This disk, vast and structured as it was, existed in a state of continuous, gradual change throughout this period of our solar system's formation. Material continued slowly spiraling inward toward the sun, drawn by gravity and by friction with the surrounding gas, even as other processes worked to redistribute material outward in certain regions. The disk was never a static structure, frozen in place, but rather a dynamic, evolving system, its overall character shifting gradually over a span of time reaching into the millions of years, even as its most fundamental features, the frost line, the general distribution of gas and dust, remained relatively consistent throughout this period of ongoing transformation. Within this vast, slowly evolving disk, then, our story now turns toward the process that would ultimately determine everything else that followed, the gradual accumulation of scattered dust grains into progressively larger bodies, a patient, probabilistic process that would, across an immense span of time, eventually produce the planets we recognize today. That process and the remarkable, almost improbable persistence it required is where our story turns next. Within the protoplanetary disk, scattered among the countless particles of gas that so vastly outnumbered them, drifted tiny grains of solid material, dust motes barely larger than the particles of smoke rising from an extinguished candle. It is worth sitting with this image for a moment, because it stands in such stark contrast to what these humble grains would eventually become. Every planet within our solar system, every moon, every asteroid began its existence as nothing more substantial than this, scattered dust, drifting largely at random through a vast, thin disk of gas surrounding a young, newly ignited star. The process by which these scattered grains eventually grew into substantial worlds is known as accretion, and it unfolded across the earliest stages of this transformation through a mechanism surprisingly simple in its basic principle. However complex its actual outcomes proved to be across the many millions of years required to complete it. Individual dust grains drifting through the disk would occasionally collide with one another, their paths intersecting as they orbited the young sun at slightly different speeds and along slightly different trajectories. Most such collisions, especially in the earliest stages of this process, resulted in very little of lasting consequence, grains bouncing apart from one another much as they had approached, their brief contact leaving no permanent trace. But not every collision ended this way. Under the right conditions, certain grains, upon colliding, would actually stick together, held in place by relatively weak electrostatic forces, the same basic kind of static attraction that might cause a balloon to cling briefly to a wall after being rubbed against fabric. This sticking was neither guaranteed nor particularly efficient, especially at first. The vast majority of collisions still resulted in grains simply bouncing apart, their combined mass still far too small, their relative velocity still too high for any lasting connection to reliably form. But occasionally, gradually particle by particle, certain grains did successfully combine, forming slightly larger clumps of material, tiny aggregates barely more substantial than the individual dust grains from which they had formed, but marking, nonetheless, the first tentative steps in a process that would, eventually, produce entire worlds. It is worth acknowledging directly, with the same honesty this account has tried to maintain throughout, that the full details of exactly how this earliest stage of accretion actually proceeded remain, even now, an area of active scientific investigation rather than entirely settled understanding. The transition from small, electrostatically bound dust clumps to significantly larger bodies, one substantial enough for their own gravity to begin playing a meaningful role in further accumulation, involves certain theoretical challenges that researchers continue working to resolve, including questions about how relatively fragile early aggregates managed to survive the higher speed collisions that inevitably occurred as they grew larger and more numerous within the disk. Current research suggests several possible mechanisms, including localized concentrations of particles within certain regions of the disk that may have allowed gravity to become significant more quickly than a purely random, particle-by-particle process would otherwise predict. This remains a genuinely active area of scientific study, and it is presented here not as a settled, fully resolved question, but as an honest reflection of where current understanding actually stands. What we can say with considerably greater confidence, based on both theoretical modeling and direct observation of protoplanetary disks around other young stars throughout our galaxy, is that this general process, small particles gradually combining into larger ones, eventually did succeed in producing bodies substantial enough for gravity itself to become the dominant force driving further growth. Once individual clumps of material grew to roughly a kilometer or so in size, sometimes referred to at this stage as planetesimals, their own gravitational pull, though still exceedingly weak compared to anything we might associate with a fully formed planet, became strong enough to reliably attract nearby material, drawing in additional dust, smaller clumps, and eventually other planetesimals, in a process that accelerated considerably once it had properly begun. This transition marks an important shift in the overall character of the accretion process. In its earliest stages, growth depended almost entirely on chance, particles happening to collide at low enough relative speeds and under just the right conditions for a fragile connection to actually form and survive. But once planetesimals had grown large enough for their own gravity to meaningfully contribute to further accumulation, growth became progressively more reliable, each successful collision making the resulting body slightly larger, and therefore slightly more capable of attracting still further material through gravity alone. It is worth pausing here to appreciate the sheer scale of patience this entire process actually required. Growing from scattered dust grains to substantial planetesimals likely required hundreds of thousands of years, an almost incomprehensible stretch of time by any ordinary human measure, and this represented only the earliest phase of a much longer process still to come. Planetesimals themselves would need to continue colliding and combining for millions of years more before anything resembling a genuine planet would finally emerge from this patient, ongoing accumulation. There is a particular quality worth noting in this process, one that distinguishes it from the more dramatic, singular events we sometimes associate with cosmic transformation. The formation of worlds at this fundamental level did not proceed through any single decisive moment comparable to the ignition of the sun itself. It unfolded instead through an almost unimaginably long accumulation of small, individually unremarkable events, countless collisions between countless particles, the overwhelming majority of them contributing nothing more than a slightly larger clump of material, barely different from what existed a moment before. Only across the full span of this process, considered together rather than as any single isolated event, does the true significance of what was occurring become properly apparent. Within different regions of the protoplanetary disk, this same basic process of accretion proceeded somewhat differently, shaped by the particular conditions present in each specific location, closer to or farther from the young sun, within the warmer inner disk or the colder, ice-rich outer disk beyond the frost line. These regional differences, though they emerged from the very same underlying process of gradual accretion we have described here, would eventually produce dramatically different outcomes, giving rise to two fundamentally distinct categories of planets, each shaped by the particular conditions present within its own corner of the ancient, swirling disk from which it formed. It is to these differences, and to the two distinct kinds of worlds they ultimately produced, that our story now turns. We return now to a boundary introduced earlier in our story, one that would ultimately prove responsible for one of the most fundamental divisions within our entire solar system. The frost line, that particular distance from the young sun beyond which temperatures grew cold enough for water and other volatile compounds to exist as solid ice rather than dispersing as gas. Within the warmer disk closer to the sun, only rock and metal could accumulate as solid material. Beyond this boundary, ice joined rock and metal as an additional and remarkably abundant building block. It is this single distinction, seemingly modest when first described, that would ultimately determine why the inner and outer regions of our solar system came to hold such dramatically different kinds of worlds. Within the inner disk, then, planetesimals continued their patient process of accretion, using only the material available to them in this warmer region, primarily silicate rock and various metals, iron chief among them. These materials, while entirely capable of forming substantial bodies through the same gradual accretion process described in our previous chapter, were considerably less abundant, in relative terms, than the combination of rock, metal, and ice available within the colder outer disk. This scarcity of raw material placed a natural limit on how large any inner planetesimal could ultimately grow, regardless of how much time remained available for continued accretion. Consider what this meant in practical terms for the planets slowly taking shape within this inner region. Mercury, Venus, Earth, and Mars, the four planets we now call the terrestrial planets, each formed through the same basic process of colliding and combining planetesimals, but each was ultimately constrained by the relatively limited quantity of solid material available within their particular region of the disk. Even Earth, the largest of these four inner worlds, would eventually reach a size only a small fraction of what the giant planets forming simultaneously in the colder outer disk would ultimately achieve. This limitation in available material also shaped the fundamental composition of these inner worlds in a more essential way, beyond simply constraining their eventual size. Formed almost entirely from rock and metal, without significant quantities of ice or other volatile compounds incorporated directly into their initial structure, the terrestrial planets emerged as dense, solid bodies, their surfaces ultimately capable of supporting the kind of firm, walkable ground so essential to everything that would eventually unfold on at least one of these four worlds. This density, this fundamentally rocky composition, stands as one of the terrestrial planet's most defining characteristics, distinguishing them clearly, in ways we will explore shortly, from the very different kind of world simultaneously forming farther out within the same protoplanetary disk. It is worth noting, too, that the inner planets faced an additional challenge beyond the simple scarcity of available material, one connected directly to the young sun's own increasingly powerful influence. As the sun continued its early, turbulent T-Tauri phase, its stellar wind grew progressively stronger, gradually sweeping away much of the remaining gas from the inner disk, particularly in the regions closest to the star itself. This meant that even if an inner planetesimal had somehow managed to grow large enough for its own gravity to begin attracting significant quantities of surrounding gas, drawing in hydrogen and helium, the way the giant planets would eventually manage in the outer disk, the opportunity to do so simply did not last long enough, in most cases, for this additional growth to actually occur. The inner planets, in other words, were constrained not just by limited solid material, but also by limited time, the young sun's own stellar wind working to clear away the surrounding gas before the terrestrial planets could grow large enough to capture any significant portion of it for themselves. Beyond the frost line, in the considerably colder outer reaches of the protoplanetary disk, an entirely different story was simultaneously unfolding, one shaped by conditions dramatically more favorable to rapid, substantial growth. Here, with ice joining rock and metal as available solid material, planetesimals had access to a considerably greater total quantity of raw building blocks, allowing accretion to proceed more quickly, and ultimately to produce planetesimals and eventually planetary cores, considerably larger than anything forming simultaneously within the warmer inner disk. This distinction in available material, seemingly modest when described in these relatively abstract terms, produced consequences of enormous significance once these outer planetesimals grew large enough to reach a particular crucial threshold, a point at which their own gravity became strong enough not merely to continue attracting additional solid material, but to begin drawing in substantial quantities of the surrounding gas as well, the same hydrogen and helium that had, until this point, remained the disk's dominant component without contributing directly to the growth of any solid body. Once an icy, rocky core within the outer disk grew sufficiently massive, generally understood to require reaching something in the range of several times Earth's own eventual mass, it crossed this threshold, and something remarkable began to happen. We will explore exactly what happened next and the enormous planets this process ultimately produced in the chapter that follows. For now, it is enough to appreciate the fundamental divide we have traced across these two regions of the ancient protoplanetary disk. Within the warmer inner disk, limited by scarce material and by the young sun's own increasingly powerful stellar wind, relatively small, dense, rocky worlds slowly took shape, worlds that would eventually become Mercury, Venus, Earth, and Mars. Within the colder outer disk, abundant ice joining rock and metal to provide considerably more raw material, planetesimals grew larger, faster, eventually crossing a threshold that would allow them to become something categorically different from their smaller, rockier siblings closer to the sun. This single distinction, rooted in nothing more than the simple physics of temperature and the particular chemistry of which compounds can remain solid under which conditions, ultimately produced the fundamental architecture we still observe within our solar system today, an inner region of small, dense, rocky worlds, and an outer region dominated by planets of an entirely different character altogether, planets so large, so different in composition, that they would come to be known quite simply as the giants. Beyond the frost line, within the colder reaches of the ancient protoplanetary disk, certain planetesimals had grown considerably larger than anything forming within the warmer inner disk, their growth fueled by the abundant combination of rock, metal, and ice available in this more distant region. As these bodies continued accumulating additional material, colliding and combining with nearby planetesimals in the same patient, gradual process described in earlier chapters, at least one among them eventually reached a threshold of profound significance, growing massive enough that its own gravity became sufficient to begin drawing in substantial quantities of the surrounding gas, rather than simply continuing to attract additional solid material as it had until this point. This transition marked the beginning of an entirely new phase of growth, one considerably more rapid and ultimately considerably more consequential than anything that had come before it. Once a planetary core within the outer disk grew large enough to begin attracting gas directly, it found itself with access to a truly enormous additional reservoir of raw material, the hydrogen and helium that had, from the very beginning of our story, constituted the overwhelming majority of the entire protoplanetary disk's total mass. Solid material, rock, metal, and ice combined had always represented only a small fraction of the disk's overall composition. Gas, by contrast, was available in vastly greater quantities, and a sufficiently massive core now found itself positioned to draw in this abundant surrounding material at a pace considerably faster than the earlier, more gradual accumulation of solid planetesimals had ever achieved. This particular planetary core, having crossed the necessary threshold before any other body within the disk, would eventually become Jupiter, ultimately growing to become the largest planet within our entire solar system, its final mass exceeding that of every other planet combined by a considerable margin. The scale of this achievement deserves genuine appreciation, because it reflects something significant about the particular conditions present within this early region of the outer disk, conditions favorable enough and timing fortunate enough for a single planetary core to grow large enough to begin this rapid gas accretion phase before the surrounding disk's gas had been depleted or dispersed. This matter of timing carries particular importance, one worth pausing on directly. The young sun's stellar wind, as described in earlier chapters, continued growing stronger throughout this early period, gradually clearing away the disk's remaining gas, a process that would eventually leave very little gas available for any further significant accretion, regardless of how large a planetary core might have grown by that point. This meant that any planetary core hoping to accumulate a substantial gaseous envelope faced a genuine race against time, needing to reach the necessary threshold mass before the surrounding gas disappeared entirely. Jupiter's core, forming relatively early and relatively efficiently within this favorable outer region of the disk, succeeded in winning this particular race, accumulating an enormous envelope of hydrogen and helium gas before the young sun's wind had cleared away the surrounding material. Saturn, forming through this same basic process but somewhat later, or perhaps somewhat less efficiently than Jupiter, still managed to grow substantially, accumulating its own considerable envelope of surrounding gas, though ultimately reaching a final mass notably smaller than its larger sibling. Together, Jupiter and Saturn represent the two so-called gas giants of our solar system, planets composed overwhelmingly of hydrogen and helium, their original rocky and icy cores now buried deep beneath layers of gas so vast that these cores represent only a small fraction of each planet's overall mass. It is worth taking a moment to properly appreciate just how different these emerging giant planets were from the small, rocky worlds simultaneously forming within the inner disk. Where Earth and its terrestrial siblings possessed firm, solid surfaces, the product of relatively modest accumulations of rock and metal, Jupiter and Saturn possessed no true surface at all in any conventional sense, their outer layers consisting entirely of gas, gradually compressing under increasing pressure as one descended deeper toward each planet's core, but never transitioning into anything resembling solid ground. This fundamental difference in structure, arising directly from the different quantities and types of material available within their respective regions of the ancient protoplanetary disk, represents one of the most significant distinctions within our entire solar system's architecture. Beyond Jupiter and Saturn, within the still more distant, still colder reaches of the outer disk, two additional planetary cores were simultaneously undergoing their own process of accretion, eventually becoming Uranus and Neptune. These two worlds, while still considerably larger than any of the terrestrial planets, and still composed predominantly of icy and gaseous material rather than solid rock, nonetheless grew notably smaller than either Jupiter or Saturn, likely a consequence of their greater distance from the Sun, where the raw material available for accretion, though still including significant quantities of ice, existed in somewhat lower density than in the regions where Jupiter and Saturn had formed, and where the overall process of accretion likely proceeded somewhat more slowly as a result. It is worth introducing here, if only briefly, a concept that later chapters will explore in considerably greater depth. The giant planets we observe within our solar system today did not necessarily form in precisely the orbital positions they currently occupy. Considerable evidence, gathered through decades of careful observation and increasingly sophisticated computer modeling, suggests that Jupiter, Saturn, Uranus, and Neptune likely underwent significant orbital migration following their initial formation, their positions shifting gradually over time due to complex gravitational interactions both among themselves and with the remaining disk material still surrounding them. This migration and its far-reaching consequences for the rest of our solar system deserves its own careful treatment, one we will return to shortly, once we have properly traced the remaining major events of our solar system's early, formative history. For now, though, it is enough to simply appreciate what these four giant planets ultimately represent. The direct product of favorable conditions within the colder, ice-rich outer disk, where sufficient raw material and sufficient time allowed certain planetary cores to grow large enough to begin capturing substantial quantities of surrounding gas, transforming what might otherwise have remained relatively modest icy and rocky bodies into the immense gas-dominated giants that continue, even now, to define so much of our solar system's overall character and structure. With both the terrestrial planets of the inner disk and the giant planets of the outer disk now having taken their essential shape, our solar system had, in its broadest outlines, begun to resemble something we might recognize today. But this early architecture remained, in many important respects, considerably rougher and more chaotic than the relatively calm, orderly system we now observe. Ahead lay a period of significant upheaval, one marked by tremendous collisions, dramatic orbital shifts, and a level of chaos that stands in striking contrast to the quiet stability we generally associate with our solar system in its present, mature form. Among the small, rocky worlds taking shape within the warmer inner reaches of the protoplanetary disk, one in particular would eventually become the focus of our entire story, the third planet from the Sun, still young, still forming, still considerably different from the world we recognize today. Early Earth, in this formative period, bore little resemblance to the planet we now call home. Its surface remained largely molten, heated both by the residual energy of its own violent formation and by the continued impact of additional material still falling inward from the surrounding disk. No oceans yet existed. No atmosphere resembling anything breathable had yet formed. It was, by any reasonable description, an inhospitable world, still very much in the earliest stages of its long, gradual transformation. It was during this particularly turbulent period, sometime in the first several tens of millions of years following the initial formation of the solar system, that Earth encountered what may have been the single most consequential event in its entire early history, a collision of such scale and violence that its consequences continue to shape our planet, quite literally, to this very day. The leading scientific explanation for this event, known as the giant impact hypothesis, proposes that a planetary body roughly the size of Mars, one that has since been given the name Theia, collided with the young, still-forming Earth. It is worth pausing here to properly appreciate the scale of violence such a collision would have represented. This was not a minor impact, of the kind Earth would go on to experience countless times throughout its subsequent history from various smaller asteroids and comets. This was a collision between two genuinely substantial planetary bodies, one roughly Earth's own size, the other comparable to Mars, colliding with a combined force almost impossible to properly convey through ordinary language. The immediate aftermath of such a collision would have been almost unimaginably violent, at least judged by the standards of anything we might picture occurring on Earth today. Enormous quantities of material, fragments of both Theia and Earth's own outer layers, would have been thrown outward from the impact with tremendous force. Some of this material vaporized entirely by the sheer energy of the collision, other portions remaining as solid or molten debris, scattered outward into the space surrounding the badly damaged young Earth. Rather than simply dispersing entirely into space, however, a significant portion of this ejected material remained gravitationally bound to Earth, continuing to orbit the battered planet in a chaotic, disorganized ring of debris, not unlike a rough, early version of the planetary rings we observe around Saturn today, though considerably less orderly and destined for a very different eventual fate. Over a relatively short span of time, astronomically speaking, perhaps only a matter of decades or centuries rather than the millions of years required for planetary formation more broadly, this orbiting debris began to coalesce, drawn together by its own mutual gravity in a process resembling, on a smaller and more rapid scale, the same basic accretion that had formed the planets themselves. The result of this coalescence was the Moon, Earth's own singular satellite, formed not gradually over millions of years through the patient accumulation of scattered material throughout the broader protoplanetary disk, but rather relatively quickly from the concentrated debris of a single catastrophic collision. This origin story helps explain several distinctive characteristics of the Moon that had, for a long time, puzzled scientists attempting to understand its formation through other means, including its relatively small core compared to Earth's own, and certain similarities in composition between lunar rock and Earth's own outer layers, similarities that align well with a moon formed substantially from material originally belonging to Earth itself, rather than an entirely separate body captured intact from elsewhere within the solar system. It is worth acknowledging, with the same scientific honesty maintained throughout this account, that certain details of the giant impact hypothesis remain subjects of ongoing research and refinement. Questions persist regarding the precise details of the collision itself, the exact angle and speed of impact, the precise proportion of material contributed by Theia versus Earth's own outer layers to the eventual Moon. But the broader framework, a massive early collision between the young Earth and another substantial planetary body, resulting in debris that subsequently coalesced into the Moon, remains the most widely supported explanation currently available, consistent with a considerable body of evidence gathered from lunar samples, computer modeling, and careful comparative analysis of Earth and Moon composition. There is something worth sitting with here, something that stands in notable contrast to much of what we have described across the earlier chapters of this account. Where the formation of planets through gradual accretion represented a patient, largely peaceful process, unfolding across immense stretches of time through countless small, individually unremarkable collisions, the formation of the Moon represented something categorically different, a single, catastrophic event of almost unimaginable violence, its consequences settled within a comparatively brief span of time, rather than the millions of years typically associated with planetary formation more broadly. And yet, despite this violent origin, the consequences of this particular collision were not purely destructive, an important distinction worth emphasizing. The Moon that emerged from this catastrophic impact would go on to play a significant, ongoing role in shaping Earth's subsequent development, its gravitational influence gradually stabilizing Earth's own axial tilt, helping to moderate the kind of extreme, chaotic variations in seasonal patterns that a planet lacking such a substantial satellite might otherwise experience across long stretches of geological time. In this sense, an event that began in violence and destruction ultimately contributed something genuinely stabilizing and beneficial to Earth's long-term development, a pattern we will see repeated in various forms across several of the chapters still ahead of us in this account. For now, though, it is enough to simply appreciate this singular, transformative event for what it represented in its own moment. A young, still-forming Earth, already scarred and reshaped by the ordinary violence of planetary accretion, encountering one final catastrophic collision, one that would leave behind, quite literally, a lasting companion, a moon that continues, even now, billions of years later, to orbit patiently overhead, a permanent reminder of one of the most consequential moments in our planet's entire early history. Having traced the formation of the terrestrial planets and the giant planets, and having witnessed the particularly dramatic collision that ultimately produced Earth's moon, our story now turns toward a broader, system-wide transformation, one considerably less localized than any single planetary collision, but no less significant for everything that followed. This transformation concerns the giant planets themselves, Jupiter, Saturn, Uranus, and Neptune, and the considerable evidence suggesting that these four enormous worlds did not necessarily remain in the same orbital positions where they originally formed. The scientific framework most commonly used to describe this period of orbital rearrangement is known as the Nice model, named for the French city where the researchers who first proposed it were working at the time. This model, developed through careful computer simulation and refined considerably over the years since its initial proposal, suggests that the four giant planets in the earliest stages following their formation occupied orbital positions considerably closer together and closer to the Sun overall than the positions they currently hold within our solar system today. According to this model, the giant planets' original, more closely spaced arrangement proved gravitationally unstable over time, particularly once interactions with the still substantial disk of remaining icy debris, material left over from the original protoplanetary disk that had not yet been incorporated into any of the major planets, began exerting subtle but cumulative gravitational influence on the giants' orbits. Jupiter and Saturn in particular eventually settled into what is known as an orbital resonance, a configuration in which their respective orbital periods around the Sun align in a simple mathematical ratio, a state that, rather than promoting long-term stability as one might initially assume, actually tends to amplify certain gravitational interactions between the two planets over time. This amplification, according to the Nice model, eventually triggered a period of significant orbital migration among all four giant planets, Jupiter shifting slightly inward toward the Sun, while Saturn, Uranus, and Neptune each migrated considerably outward, their final positions eventually settling into something much closer to the arrangement we observe today. This migration did not occur instantaneously, but rather unfolded over a period that likely spanned many millions of years, the giant planets' orbits gradually shifting through a complex, ongoing series of gravitational interactions, both among the four planets themselves and with the substantial population of smaller icy bodies still populating the outer solar system at this time. It is worth pausing here to properly appreciate just how significant this kind of large-scale orbital rearrangement actually represents, particularly in contrast to the relatively calm, stable orbits these same four planets maintain today. We tend, quite naturally, to think of planetary orbits as fixed, permanent features of our solar system, established once during the initial process of formation and remaining essentially unchanged ever since. The Nice model, along with the considerable evidence supporting it, suggests something rather different, a solar system considerably more dynamic in its early history than the relatively settled, predictable system we now observe, one in which even the largest planets, Jupiter foremost among them, underwent significant positional change during the millions of years following their initial formation. This migration carried consequences extending far beyond the giant planets themselves, ultimately affecting nearly every other body within the solar system, including the smaller icy objects still populating the outer reaches of the original protoplanetary disk. As Jupiter, Saturn, Uranus, and Neptune shifted through their respective migrations, their combined gravitational influence would have significantly disrupted the orbits of countless smaller bodies throughout the outer solar system, scattering some of this material into entirely new orbital configurations, flinging other objects outward into the distant, sparse region we now call the Oort cloud, and most significantly for the specific consequences we will examine in our next chapter. Redirecting a substantial quantity of this disrupted material inward toward the inner solar system and toward the four rocky, terrestrial planets that had, by this point, already largely completed their own initial formation. It is worth acknowledging, once again with appropriate scientific caution, that the NICE model, while representing the most widely supported current explanation for the giant planet's apparent orbital migration, remains an active area of ongoing research, with various refinements and alternative versions of the model continuing to be developed and tested against accumulating observational evidence. The broad outline significant early migration among the giant planets, followed by substantial disruption to the surrounding population of smaller bodies, enjoys considerable scientific support. But the precise details, the exact timing, the specific sequence of gravitational interactions involved remain subjects of continued investigation and refinement. What can be said with reasonable confidence, however, is that this period of significant orbital rearrangement represents a genuinely important chapter in our solar system's early history, one that helps explain a considerable range of otherwise puzzling observations, from the particular orbital characteristics of certain small bodies within the outer solar system, to, as we will explore directly in our next chapter, a period of intense bombardment that Earth's own moon experienced sometime after its initial formation, a period whose evidence remains visible, quite literally, in the moon's own heavily cratered surface, still observable to anyone who looks up toward it on a clear night, even now, billions of years after these dramatic events first took place. Our solar system, then, in these early formative millions of years, was a considerably more dynamic, considerably more unsettled place than the calm, orderly system we generally picture today. Giant planets shifted position. Countless smaller bodies found their orbits dramatically disrupted. And somewhere within the inner solar system, the young terrestrial planets, Earth very much among them, were about to experience the direct consequences of this widespread orbital upheaval, in the form of a bombardment considerably more intense than anything they had experienced since the earliest, most active stages of their own initial formation. As the giant planets settled gradually into the more widely spaced orbital arrangement described in our previous chapter, the disruption their migration caused rippled outward through the surrounding population of smaller bodies, sending a considerable quantity of icy and rocky debris, material that had remained relatively undisturbed within the outer solar system since the earliest stages of planetary formation, tumbling inward toward the sun, and toward the four rocky worlds occupying the solar system's innermost region. The period that followed, generally dated to somewhere around 3.9 billion years ago, though the precise timing remains a subject of ongoing scientific refinement, is known to astronomers and planetary geologists as the Late Heavy Bombardment, a term describing what appears to have been a significant spike in the rate at which asteroids and comets collided with the inner planets Earth, Mars, Mercury, and perhaps most usefully for scientists attempting to study this period today, the Moon. It is worth explaining, before going further, exactly why the Moon occupies such a central place in our understanding of this particular chapter of solar system history. Earth, over the billions of years since this bombardment occurred, has experienced continuous geological activity, plate tectonics, erosion, volcanic resurfacing, all of which have gradually erased the vast majority of direct physical evidence from impacts this ancient. The Moon, by contrast, lacking any comparable geological activity, lacking any atmosphere capable of producing erosion, has preserved its impact record with remarkable fidelity, its heavily cratered surface remaining essentially unchanged since these ancient collisions first occurred. When scientists look up at the Moon today and examine in detail the density and distribution of its craters, they are looking, in a very real sense, directly at physical evidence of this ancient period of intense bombardment, preserved essentially unaltered across more than 3.5 billion years. Samples returned from the Moon's surface, gathered during the Apollo missions of the late 1960s and early 1970s, allowed scientists, for the first time, to directly examine and date lunar rock formed or altered during major impact events. Careful analysis of these samples revealed something notable: a surprising concentration of impact-related ages clustering around the same general period, roughly 3.8 to 4 billion years ago, rather than showing a more gradual, steadily declining rate of impacts extending smoothly backward from the Moon's initial formation. This clustering, along with corroborating evidence gathered from careful crater counting analysis across different regions of the lunar surface, forms the primary observational basis for the late heavy bombardment hypothesis as it is generally understood today. The connection between this apparent spike in impacts and the giant planet migration described in our previous chapter offers one compelling explanation for why this particular bombardment occurred when it did, rather than simply representing a continuation of the same gradual decline in impact rates that would be expected as the young solar system's leftover debris was steadily incorporated into existing planets or ejected entirely over time. If the NICE model's broad outline is correct, the significant gravitational disruption caused by Jupiter, Saturn, Uranus, and Neptune shifting through their respective orbital migrations would have scattered a substantial quantity of previously stable material inward, toward the inner solar system, potentially explaining why the inner planets experienced a notable increase in bombardment during this particular period, rather than a smooth, continuous decline extending back to the earliest days of planetary formation. It is important, however, to acknowledge directly that this connection between giant planet migration and the late heavy bombardment, while representing one of the more compelling explanations currently available, remains a subject of genuine scientific debate rather than fully settled consensus. Some researchers have raised questions about various aspects of the evidence, including whether the apparent clustering of ancient lunar impact ages might partly reflect limitations in the sampling locations chosen during the Apollo missions, rather than necessarily reflecting a true, solar system-wide spike in bombardment during this specific period. This represents precisely the kind of genuine scientific uncertainty this account has tried to acknowledge honestly throughout, a hypothesis with considerable supporting evidence and explanatory power, but one that continues to be tested, refined, and in some respects questioned, as additional evidence and more sophisticated analytical techniques become available to researchers. Setting aside these ongoing questions of precise interpretation, what can be said with reasonable confidence is that the inner solar system, sometime in the several hundred million years following the initial formation of the planets, experienced a period of considerably more intense bombardment than the relatively quiet, stable conditions we observe today, whatever its precise cause or exact timing may ultimately prove to have been. Earth itself during this period would have experienced impacts considerably more frequent and considerably more severe than anything the planet has faced during the more recent, relatively quiet billions of years of its subsequent history, its surface repeatedly scarred by collisions with asteroids and comets arriving from across the solar system. This period of intense bombardment carries a particular significance worth highlighting directly, one that connects this seemingly destructive chapter of our solar system's history to something considerably more constructive. Many of the icy bodies disrupted during this period, particularly comets originating from the colder, more distant regions of the outer solar system, carried within them substantial quantities of water, along with various other volatile compounds and organic molecules, the basic chemical building blocks from which more complex biological chemistry might eventually develop. Some researchers suggest that a meaningful portion of the water now filling Earth's oceans, along with certain organic compounds relevant to life's eventual emergence, may have arrived precisely during this period, delivered by the very bombardment that, in more immediate terms, would have represented a period of considerable violence and destruction for the young Earth. This possibility, again offered with appropriate acknowledgement of the genuine scientific uncertainty still surrounding many of its details, adds a particular layer of significance to this otherwise violent chapter of our solar system's early history. Earth, already possessing some quantity of water and volatile material from its own initial formation within the protoplanetary disk, may have received a further significant contribution during precisely this period of intense bombardment, material arriving not as a gift, in any sense the young, battered planet could have appreciated at the time, but nonetheless contributing, whether primarily or only partially, to the eventual conditions that would, across the billions of years still to follow, prove suitable for the emergence of life itself. As the intense bombardment described in our previous chapter gradually subsided, its frequency declining across the following hundreds of millions of years back toward the relatively quiet conditions that would eventually characterize our solar system's long-term, mature state, another significant transformation was simultaneously drawing to its own conclusion, one concerning not the inner planets directly, but the vast quantities of gas that had, since the very earliest stages of our story, filled the space surrounding the young sun and its still-forming planets. Throughout the many millions of years required for planetary formation, the young sun had continued its early, turbulent T-Tauri phase, its stellar wind blowing considerably stronger than the relatively gentle solar wind our present-day sun produces. This powerful early wind, along with the sun's own intense radiation, had been working, gradually and continuously, to push the remaining gas of the original protoplanetary disk outward, away from the inner solar system, and eventually away from the solar system entirely. By this stage in our story, the majority of this original gas had in fact already been cleared away, a process that had been unfolding gradually throughout the many millions of years already described across the preceding chapters, but which now, with planetary formation itself largely complete, was approaching something closer to its final, essentially total conclusion. Where once an enormous, extended disk of hydrogen and helium had surrounded the young sun, providing the raw material that Jupiter and Saturn in particular had drawn upon so extensively during their own formation, only scattered remnants now remained, thin and increasingly insignificant compared to the disk's original, considerable extent. This dispersal of the remaining gas marks a particularly significant threshold in our solar system's development, one worth pausing to properly appreciate. With the gas gone, the fundamental process of planetary formation that had driven every major event described across this entire account, gravitational collapse, accretion, gas capture by the giant planets, effectively came to its natural conclusion. There simply was no longer enough raw material remaining, in either gaseous or substantial solid form, for any further significant planetary growth to occur. Whatever planets, moons, and smaller bodies existed at this point, having formed through the many millions of years of accretion and gravitational interaction already described, would represent, in their broad outlines at least, the solar system's essentially final architecture, the same fundamental arrangement of worlds we continue to observe today. It is worth noting, too, that this clearing of the surrounding gas carried consequences extending beyond simply ending further planetary growth. The gas that had, until this point, continued filling the space between and around the forming planets had also exerted a subtle, continuous drag on the orbits of smaller bodies still moving through this material, gradually influencing their trajectories in ways that added a further layer of complexity to the overall dynamics of the young solar system. With this gas now largely dispersed, orbits throughout the solar system would have begun settling into somewhat more stable, more predictable patterns, no longer subject to this particular ongoing influence, even as other sources of gravitational disruption, including the continued, gradual effects of the giant planet's earlier migration, continued shaping the broader system for some time yet. There is a particular quality worth appreciating in this stage of our story, a sense of settling, of gradual quieting, that stands in notable contrast to the intense, often violent activity described across the several preceding chapters. Where earlier chapters traced dramatic collisions, significant orbital migrations, and periods of intense bombardment across the inner solar system, this chapter describes something considerably calmer, the slow, patient dispersal of the last remaining traces of the cloud from which everything else in our story had originally emerged. It is, in its own quiet way, a kind of exhaling tension, gradually releasing after the considerable turbulence and violence of the preceding hundreds of millions of years. Picture, if you will, this transition as it might have appeared, could any observer have witnessed it directly. Where once an enormous glowing disk of gas and dust had surrounded the young sun, extending outward across a distance considerably greater than the orbit of Neptune, illuminated faintly by the light of the newly ignited star at its center, only clear, comparatively empty space now remained, the sun's light traveling outward largely unimpeded, reaching the various planets, moons, and smaller bodies now occupying their own increasingly stable orbits, no longer filtered or scattered by the dense, swirling material that had once filled this same space so completely. This moment represents something close to a genuine milestone in our solar system's long history, the conclusion of the active, formative period that had, across the many millions of years already described throughout this account, transformed a diffuse, unremarkable cloud of interstellar gas and dust into a fully formed system of planets, each shaped by the particular conditions present within its own region of the original protoplanetary disk. What remained following this final clearing of the surrounding gas was recognizably a solar system in the fuller sense we understand the term today. 4 rocky, terrestrial planets occupying the warmer inner region, 4 much larger giant planets occupying the colder outer region, along with countless smaller bodies, asteroids, comets, and other debris, scattered throughout the remaining space, remnants of the same formative process that had produced everything else within this now largely settled system. Ahead, though the most dramatic and eventful chapters of our solar system's earliest history had now largely concluded, lay a considerably longer period still, one measured not in millions but in billions of years, during which the various planets, having settled into their essentially final positions and their essentially final compositions, would continue their own separate, gradual evolution, each following its own particular path forward from this shared, common origin. That long, considerably quieter period, and the deep stability it would eventually establish, awaits us in the chapters ahead. With the protoplanetary disk's gas now largely dispersed, and the intense bombardment of the solar system's earliest hundreds of millions of years gradually subsiding, our story arrives at a transition considerably different in character from anything described across the preceding chapters. What followed the dramatic formative period we have traced so far was not another single, definable event, but rather something closer to an extended settling, a long, gradual easing into the kind of deep stability that continues to define our solar system even now, billions of years later. This transition unfolded slowly, without any clear boundary marking its beginning. As the giant planets completed the bulk of their earlier migration, and as the remaining population of asteroids and comets was gradually thinned, some incorporated into existing planets and moons through continued impacts, others ejected entirely from the solar system by gravitational encounters with the giants, others still settling into the relatively stable reservoirs we now recognize as the asteroid belt and the more distant Kuiper belt. The overall rate of significant gravitational disruption throughout the solar system declined considerably, approaching something much closer to the calm, orderly conditions we observe today. It is worth pausing to properly appreciate the scale of time involved in this settling, because it differs so considerably from anything within ordinary human experience. Where the earlier chapters of our story unfolded across hundreds of thousands or millions of years, dramatic by any human measure but still, in cosmic terms, relatively brief, the stability our solar system gradually achieved during this period would go on to persist across billions of years, an expanse of time so vast that the entire history of life on Earth, from its earliest microscopic beginnings through to the present moment, represents only a portion of the calm that followed this ancient formative chaos. Within this long stability, the planets settled into orbits that would remain, with only minor variations, essentially unchanged across the enormous span of time still to come. Earth found its place third from the Sun, positioned within what scientists sometimes call the habitable zone, a region neither too close to the Sun's heat nor too far into its cold, where conditions might allow liquid water to persist on a planet's surface, a possibility whose full significance had not yet, at this stage of our story, been realized in any way. There is a particular kind of grace in this long, quiet period, one worth sitting with before our story reaches its conclusion. After the violence of planetary accretion, after the catastrophic collision that formed the moon, after the intense bombardment that scarred the inner planets, the solar system settled finally into something resembling peace, a stability that would provide, across the billions of years still ahead, exactly the kind of steady, dependable conditions that slow processes, like the emergence of life itself, would eventually require in order to unfold. We return in this final chapter to the one planet within our entire solar system, whose story would eventually diverge most profoundly from all the others, not through any difference in its basic formation, which followed the same fundamental process of accretion described across the earlier chapters of this account, but through what would gradually happen upon its surface, once the chaos of formation had finally given way to the long stability just described. Early Earth, in the immediate aftermath of the collision that formed the moon, remained an inhospitable world by any reasonable standard, its surface still largely molten, its atmosphere, if it could even be called that at this stage, composed of gases entirely unsuitable for anything resembling the world we know today. Gradually, though, across the many millions of years that followed, this young planet began, slowly and patiently, to cool. Its molten surface, exposed to the cold of surrounding space, began solidifying into the first thin, unstable fragments of what would eventually become a proper crust. As Earth continued cooling, volcanic activity, itself a product of heat still trapped deep within the planet's interior, released considerable quantities of gas from below the surface, water vapor, carbon dioxide, and various other compounds gradually accumulating to form Earth's first genuine atmosphere, thin and inhospitable by later standards, but a beginning nonetheless. Some portion of the water now present within this early atmosphere had likely been present within Earth's own original formative material, incorporated directly during the planet's initial accretion. Some further portion, as discussed in our earlier chapter on the late heavy bombardment, may well have arrived later still, delivered by the comets and icy asteroids that struck Earth with such notable frequency during that particularly turbulent period. As Earth's surface continued cooling, eventually growing cold enough for water to persist in liquid form rather than immediately evaporating back into the surrounding atmosphere, rain began to fall, likely for the first time in the planet's history, gradually collecting within the lowest regions of its still-forming crust. Across a span of time difficult to fully specify with precision, but likely unfolding over many millions of years, these gradually accumulating waters would eventually become the first oceans, vast bodies of liquid water covering significant portions of Earth's surface, a feature that, as far as current evidence suggests, remains genuinely unique among the 8 planets of our solar system. No other world sharing this particular, quietly extraordinary characteristic. It is worth pausing in these final moments of our long account to properly appreciate what this transformation actually represents. A planet that began, like every other body within our solar system, as scattered dust within an ancient, unremarkable molecular cloud, had gradually, across billions of years and through an almost unimaginable sequence of formative events, become something capable of holding liquid water upon its surface. A planet no longer simply rock and metal, but one now possessing the basic conditions that would, in time, allow something as remarkable as life itself to eventually take hold. We will not trace within this particular account the further story of exactly how life first emerged from these early, still-forming oceans, a story every bit as remarkable as the formation of the solar system itself, and one that deserves its own careful, patient telling in its own right. For now, it is enough to arrive here at this quiet, early moment, a young Earth still cooling, still settling into the stable conditions that would define its long future, its first oceans just beginning to gather within the low places of its newly formed crust, beneath a sky lit by a sun no longer nearly as turbulent as it had once been in its own early, formative years. There is something worth carrying with us as this particular account draws to its close. Everything we have followed across these 14 chapters, the collapse of an ancient cloud, the ignition of a star, the slow accretion of scattered dust into planets, the violent collision that gave Earth its moon, the long, patient stability that followed, all of it led eventually to this quiet, unassuming moment, a young planet with water gathering gently upon its surface, waiting, though it could not have known it was waiting, for something extraordinary still to come. Every atom within your own body, whoever is listening to this now, was once scattered somewhere within that same ancient cloud we began this account describing, drifting quietly through the galaxy long before there was any sun, any Earth, any story at all. Across billions of years, through processes as violent as planetary collision and as patient as the slow settling of stardust, that material eventually found its way here, to this particular moment, to this particular planet, circling this particular star. We are, each of us, made from the same material that once drifted, formless and unremarkable, through the quiet dark. And somewhere within that long, patient journey from scattered dust to living, breathing wonder, something remarkable happened. Something worth remembering gently as you drift now toward your own quiet rest.